Hi, I'm Herb Gross, and welcome once again to Gateways to Mathematics. We're going to start Module 9 today, and in a sense, congratulations for graduating. We have finished Part 1 of the course. You are now qualified to go out and apply your arithmetic skills, but now comes the bad news. We have to know how to apply them, and that's what the rest of this course will be devoted to. You see, we've spent a lot of time talking about how you compute rates. Now the question is, where do they come up? And what kind of rates are there? I remember many years ago when my oldest boy was, maybe about 4 or 5 years old, we were watching a football game Thanksgiving morning. I think it was the Green Bay Packers against the Chicago Bears. And the announcer was reading off the starting lineups. And he said, Jones, left tackle, 280. Smith, right tackle, 275. O'Hara, center, 265. And my son said, Jeepers, Dad, no wonder them guys are so good. Look how old they are. And what he had done was made a very interesting assumption. He had assumed that if you're twice as old, you're twice as good. See, that's called a constant rate. You see, unfortunately in life, most rates are not constant. You're not twice as smart when you're twice as old. In fact, maybe that's where the generation gap comes from. A person thinks that because he's been on the job twice as long, he knows twice as much. He confuses 20 years of experience with 1 year of experience 20 times. On the other hand, we have to start someplace. And the way we get into regular rates is to start with constant rates. And since you've graduated, I'm going to use some big words today that are going to make this a fun topic. Let's go over to the board and really get into it today. The two topics that I'm going to talk about to some extent today are known in higher mathematics as linearity and dimensional analysis. Doesn't that sound impressive? Linearity is basically another word for constant rate. And dimensional analysis is going to be an attempt by me to show you an easy way to keep track of computing rates. Let me show you what I mean by linearity. Suppose you're buying items at $2 each. We'll make a little graph here. Don't worry about the fact that we haven't done graphs before. What I'll do is on this line, I'll indicate the number of items. And on this line, I'll indicate how much the items cost. So if I don't buy anything, it doesn't cost me anything. If I buy one item, that's going to cost me $2. If I buy a second item, that's going to cost me $2 more. And you see what's happening? Every time I move one to the right, I move two up. See, one to the right, two up, one to the right, two up, one to the right, two up. And if I look at where all these points are, they're going to lie on a straight line, and hence the word linearity. Now, in real life, most situations are not linear. For example, if we were graphing the learning process, assuming that you're born with no knowledge, you learn gradually, maybe eventually taper off, then maybe you beep out or something, whatever happens, this is the end. But basically, the knowledge doesn't go linearly. And what the subject called calculus is all about is based on linearity. What we're saying is that even in the whole picture, even though this may not be linear, globally this may not be linear, locally life is linear. Basically, what the subject of calculus does is it takes a point on a non-straight line, draws in what we call a tangent line, and basically says, if you stay close enough to this point, the straight line that's tangent to the curve looks like the curve itself. And the reason I'm giving you all of this is for you to take heart. This may look like very elementary stuff, but it's of small things that big things are made. If it wasn't for the 26 outs in the baseball game that were routine, the 27th spectacular out wouldn't have amounted to much because the game would have been out of hand by then. What I want you to understand is that as you learn this material, you will be getting the background for all of higher mathematics. That sooner or later, everything comes back to arithmetic. So let's keep that in mind, and let's go on, and let me show you now where dimensional analysis comes in. Look. So let's go back to a very easy problem. I say 8 divided by 2. We know that that's 8 over 2. And based on our work with common fractions, we said what? 8 is 2 times 4. 2 is 2 times 1. Since 2 is a common factor of numerator and denominator, we can cancel it. We get 4 over 1, or 4 for the answer. You say, big deal. That's baby stuff. What's that got to do with linearity and dimensional analysis? Well, the point is this. Suppose I take 8 miles divided by 2 miles. This is a tricky question. What's the answer to this problem? 8 miles divided by 2 miles. Be careful. The 8 divided by 2 is 4. The tricky part is don't say 4 miles. The answer is 4. Remember, when you're dividing like denominations, the quotient tells you the relative size. You see, what this says is that 8 miles is 4 times as big as 2 miles. Another way of looking at it is 4 times 2 miles is 8 miles. You have to take 2 miles 4 times to get 8 miles. You see, if you put miles over here, the problem would be 4 miles times 2 miles, and that's called 8 square miles. But if I told you more about that, we wouldn't need module 11. So we'll wait until module 11 until we get there. But here's the thing I wanted you to see. Suppose I agree to write this as a fraction the same way as when there were no nouns present. In other words, just like I wrote 8 divided by 2 is 8 over 2, suppose I write that 8 miles divided by 2 miles is 8 miles over 2 miles. What I can do is I can cancel the 2 just as I did before, but I can also cancel the miles. Now, why can I do that? Not because it's logical, not because it's self-evident, but because it agrees with the right answer. That's the bottom line. When we have a theory, and the theory disagrees with what's going on in the real world, it's the theory that we have to change, not the real world, though we can work on that too. You know the old story, according to the principles of aerodynamics, a bumblebee can't fly. But the bumblebee doesn't know the principles of aerodynamics. So it goes on flying and even has time to make some honey on the side. Basically, the idea I'm trying to bring out here is there will come a time when the only reason that you need to justify a shortcut is to know that it gives you the answer that agrees with the real world. Okay? And again, let me make sure you understand this. See, if I write 8 miles divided by 2, see, the 8 divided by 2 is 4, but now the answer is 4 miles. You see, if you cut 8 miles in half, each half is 4 miles. You need to take what? 4 miles twice to get 8 miles. You see, if you left the miles out here, 4 times 2 is 8, not 8 miles. And you see, 8 miles over 2, we still cancel the 2 into the 8, but the label miles remains. And you say, well, what's so great about that? Well, let me show you how this simplifies some of the computations that we have to do. Here's a problem. It says simplify 2 pints per quart times 4 quarts per gallon. There was my Boston accent, not quarts, quarts. Well, what the heck? You get what you pay for, all right? Let's write this in the new language. First of all, whenever the adjective is missing, it's always assumed to be 1. So according to our new language, 2 pints per quart is 2 pints divided by 1 quart. 2 pints over 1 quart. And 4 quarts per 1 gallon is 4 quarts over 1 gallon. Now look at this multiplication problem. Quarts in the denominator cancels with quarts in the numerator. And here we have to use some broken English. In dimensional analysis, we don't distinguish singular from plural. It's just the noun that matters. We either say 4 quart or 1 quarts. But in here, all we do is worry about the dimensions. And look what happens. What's left now? The numbers are 2 times 4, which is 8. 1 times 1 is 1, but we leave that out. The numerator is pints. The denominator is gallon. Pints over gallon is called what? Pints per gallon. A fact which checks with the real world. There are 2 pints to a quart, 4 quarts to a gallon. Therefore, there are 8 pints per gallon. Let's do a couple of more problems this way. And again, don't lose track of the main issue. You may very well know easier ways of doing this problem. Remember in our first lecture we talked about the psychology of learning, that sometimes 2 different problems use the same mathematical procedure. But one problem doesn't bother us because we're comfortable with the numbers and the language, and the other one bothers us because the vocabulary or the numbers are strange. So I'm deliberately picking very, very simple numbers to introduce the concept. Problem number 2 says, if you can buy 1 cap for $4, how many caps can you buy for $12? Now this is a simple enough problem, but notice the number of people who shuffle numbers. They see a 4, they see a 12, they sense that somehow the 4 and the 12 have to come into the problem. They say, maybe I'll add them, what the heck, 16. Somebody else says, well, I'll multiply them, I'll get 48. Notice that even though we're allowed to use a calculator in this course now, that was the other thing we got promoted to. Now that you know how to work with rational numbers, you can use the calculator. But the calculator won't help you get the right answer if you don't know what to tell it. Okay? So here's the point. The point is you can say, well, let's see. Since it's $4 per cap, every cap costs me $4, so if I multiply the number of caps by $4, that will give me the total cost. But now the $12 is the total cost. If I replace the cost by $12, the number of caps is the unknown. This looks like blank, not looks like, this becomes blank times 4 equals 12, which looks like a multiplication problem, but because the blank is one of the factors, it's a division problem, so the answer is what? 12 divided by 4, which is 3. And how were you supposed to know to divide rather than to multiply? Here's where dimensional analysis comes in. Go back to about the 3rd grade, where for the first time you were taught fill in the blank. What you're going to do is go back to this problem, and wherever you don't know something, that's called the blank. See, how many caps, that's blank caps, can you buy for what? $12. So somehow what we want to do is to convert $12 into a number of caps. We say $12 equals blank caps. Now watch how this works. The given label is dollars. The label we want is caps. So we put on our thinking cap and we say, look, I want to get rid of dollars and convert to caps. Since dollars are in the numerator, I get rid of them by putting them into the denominator. And now I put caps over here. What's the relationship between dollars and caps? We were told that it's $4 for each cap. You see, no matter whether the dollars is in the numerator or the denominator, the 4 modifies dollars, the 1 modifies caps. Now look what happens. The dollars cancel, 4 goes into 12 3 times, and the answer is 3 caps. Okay? The same answer that we got this way. See, I don't care which way you do it. All I'm saying is if you say to yourself, gee, I don't know whether I'm supposed to divide or multiply, this method will take care of it for you. Watch. Let me word the same problem. I'm going to use the same numbers, but I'm going to make a subtle difference. Let me read problem 3 to you, then have you compare that with problem number 2. If you can buy 1 cap for $4, how much will 12 caps cost? You see, how does this differ from problem 2? Problem 2 says if you can buy 1 cap for $4, how many caps can you buy for $12? You see the difference? The 12 in problem 3 is modifying caps, but in problem 2, it was modifying dollars. And that small difference is the difference between multiplying by 4 and dividing by 4. Now you see, one way of doing it is we still know that the number of caps times 4 is the cost. Since the number of caps is now 12, you see before the 12 replaced the cost, now it replaces the cap. 12 times 4 is 48, so the answer is $48. But watch how my new method works. I say, look, I'm given 12 caps, and I want to find out how many dollars that costs. I always put the thing over 1 to suggest a fraction for you. I want to convert from caps to dollars. Since caps is in the numerator, I want caps to be in the denominator. That will make them cancel. Now I put the dollars in the numerator. This is an abbreviation I learned from my son. He always puts the dollar sign after the amount. And I laughed at him when he first did it. But boy, it sure simplifies working with the labels when you do it that way. At any rate, watch this. It's still where? $4 per cap. And the 4 still modifies the dollars, but since the dollars are in the numerator, that's where the 4 goes. Now the caps still cancel, but what happens now? 12 times 4 is 48. You see, the scholar's dream to get the answer without being able to think. All you have to do here is what? Put the labels in the right place. Let's do a few more problems this way. Here's one. If you travel at a speed of 50 miles per hour, how far will you go in 2 hours? Hopefully, again, this is a very simple problem for you to do. You say, well, if I'm going 50 miles in 1 hour, in 2 hours I will go twice that distance. So you didn't multiply 50 by 2. You said 50 miles per hour times 2 hours is 100 miles. Watch how this works the new way with dimensional analysis. The question says, how far will you go in 2 hours? Well, in terms of fill in the blank, 2 hours corresponds to, 2 hours is equal to blank miles. And what do we do here? The given label is hours. We want miles. Since hours occur in the numerator, we put them into the denominator to cancel. Put miles into the numerator. How many miles are we going per hour? 50 miles per hour. So the 50 modifies miles. See, I don't care whether miles is in the numerator or the denominator. I'm just following the miles. Wherever the miles appear, that's where I put the 50. Now watch what happens here. The hours cancel. 2 times 50 is 100, and the label is miles. Notice the denominator really should say 1 times 1 is 1, but any number divided by 1 is itself. And here's the key point. Here's the key point that makes constant rates a little bit tricky. This is a very artificial problem. What's the likelihood that you're going to travel 2 hours and move at 50 miles per hour all the time? Especially if there's a red light and 5 cars are ahead of you. In Boston, that doesn't stop anybody, but basically the idea is what? You don't usually move at the same rate of speed. See, you don't usually have see, you might be able to buy 10 hats at $4 each, but you don't usually move the same number of miles every unit of time. See, this is the key point. How realistic is it to assume that your speed remains constant? In fact, how did the guy probably figure out that he was traveling 50 miles per hour? He probably said, hey, I went 100 miles in 2 hours, so that's 50 miles per hour. See, let's look at the problem from a different perspective, and I want to introduce to you something called average speed. See, here's a more realistic approach. See, you can take your odometer and see how far you traveled. And you can take your watch and see how long it took you. So you could say, hey, I traveled 100 miles in 2 hours. What was my average speed during this time? Speed is still miles per hour. Miles is 100 in this case. Hours is 2. Per still means divided by. 100 divided by 2 is 50. So the answer still comes out to be 50 miles per hour, but we call that the average speed. And the reason we call that the average speed is that there are lots of ways that you can go 100 miles in 2 hours. Well, for example, maybe you went 53 miles the first hour and 47 miles the second hour. That would still be what? 100 miles in 2 hours. You see, any trip that you make in which you go 100 miles in 2 hours has as its average speed 50 miles per hour. Let me give you something that as students is probably more relevant to you. Let's see if we can figure out how to work out grades. You have a course in which there are 5 tests. On the first 4 tests, you score 82, and these are all out of 100. They're all equally weighted. No tricks here. You score 82, 72, 84, and 73. And you're aiming to get an 80 average in this course. So you've got 4 tests in, 1 test to go, and now the question is, what do I have to get on this 5th test so that my average will be 80? Now we have to ask ourselves, what does it mean to say that the average is 80? It means that you scored as if you got 80 points on each test. See, if you had scored the same number of points on each test, it would have been 80 points per test. How do we work that out? We say, okay, if you have an average of 80, that means you're getting 80 points for each quiz. You're taking 5 quizzes, so you're going to get what? 80 points 5 times, so that's 400 points. In other words, on 5 quizzes, to say that you want the average to be 80, all you have to do is score 400 points. No matter how that 400 points is distributed, 400 points on 5 tests gives you an average of what? 80 points per test. 400 points divided by 5 tests is 80 points per test. Now watch how shrewd we are. No algebra, no calculus, just plain old module 1 or 2. All we're going to do is what? We'll add up all of our grades. That takes us all the way back to module 2. We add these numbers up, we get 311. How many points do we need? 400. Aha, we got to figure out what do you add on to 311 to get 400. That makes it a subtraction problem. We subtract 311 from 400, and that gives us 89. And what that says is, if you were to score 82, 72, 84, 73, and 89, you would have got the same average as the person who scored 80, 80, 80, 80, and 80. And in fact, that in very rough form measures to some extent what statistics is all about. Can you notice that these 2 students have the same average, yet their performances are quite different? This student didn't even get an 80 once and is still averaging 80. See, one of the things that we do in statistics is we figure out how much each of the individual scores deviates, so to speak, from what we call the central theme, the central limit. In other words, how much does each of these differ from 80 by? Because the bigger the deviations, the less reliable, in a sense, the average is. But at any rate, here's the thing I wanted to point out to you. In this module, you're allowed to use a calculator. Now, look at how easy this arithmetic was. I didn't need a calculator for that. But even if I had the calculator, if I didn't know what operations I was supposed to do, I couldn't solve these problems. We'll have another tape later, another lecture, to show you all the kinds of tricky problems that come up where if you had the best computer in the world, you're not going to be able to solve the problem unless you understand what the problem is really asking you to do. Okay? But at any rate, in this particular course, we don't want to deal, not course, in this particular module, we don't want to deal with average rates, we want to deal with constant rates. And among the well-known constant rates are such things as 60 minutes per hour, 24 hours per day, 5 cents per nickel, 12 inches per foot, the standard tip, which is 15% or 15 cents per dollar. See, those are rates that don't change. Those are rates that remain the same. There are lots of constant rates. In the rest of this course, we'll always assume that we're dealing with, I keep saying course, in the rest of this module, we'll always assume that we're dealing with constant rates, okay? And let's just do a few more problems this way, just to get the hang of it. You need a plumber for 20 hours. At $15 per hour, how much will it cost? One of my camera people just told me you can't get a plumber for $15 an hour. But I didn't tell him what I wanted the plumber for. $15 an hour was reasonable. Well, look, this is an easy problem. I'm not asking you to use a calculator here. I'm not asking you to use a fancy formula. All you're saying is what? Look, every hour I have the plumber, it's costing me $15. I'm having him for 20 hours, so it's going to be the 20th multiple of 15. In other words, I'm paying $15 20 times, that's $300. Well, believe it or not, there are people out there who panic when they think mathematically. And watch how dimensional analysis helps us here. Okay? See, a lot of people just say what? $15 times the number of hours is the cost per plumber. But that already, if you have a language anxiety about math, that already starts to look like a formula. On the other hand, filling in the blank, you start to see in geography tests, history tests, literature tests, that's not scary. So what are we going to do here? The given label is hours. We want dollars. Since hours is in the numerator, we put it in the denominator. Now what's the problem here? What is the relationship between dollars and hours? And we're told in this problem that you're paying what? $15 per 1 hour. See, the 15 modifies dollars. Now we cancel the common denomination. 20 times 15, you see, is 300. We can put that right in here. And the label automatically comes out to be dollars. You see, with dimensional analysis, you don't even do the arithmetic until you're sure the label is right. See, watch the subtle change. In problem number 8, it says you have $375 in the budget for a plumber. At $15 per hour, how many hours can you hire the plumber for? See, what happens now is that instead of being given the number of hours and finding the cost, you're given the cost and want to find the number of hours. That would be a division problem. But doing it our way, you say what? $375 gets you how many hours? $375 equals blank hours. And how do we solve the problem now? Since dollars are in the numerator, we want to put dollars in the denominator. And since the given label is hours, we want hours to come in here. We do a quick check. The dollars will cancel. The label is in hours. We're all set. What's the relationship between dollars and hours? It's still $15 per 1 hour. Look what happens. I just put the 15 where the dollars are. I'm not worried about that. But you see, now that the 15 is in the denominator, what does that tell me to do? You divide by the denominator, multiply by the numerator. I divide 15 into 375, and the answer is 25 hours. See, with a calculator, I can enter 375, press the division sign, enter the 15, hit the equal sign, and I'll get 25. But I have to know that I want to divide 375 by 15 before the calculator will help me. And even with the calculator, and even with all of our common sense, we have to be even more careful. You have to read problems very carefully. No matter how many age you have, no matter how many advantages you have, life is known for being able to turn up a situation that you still can't cope with. And let's watch another type of problem this way. This one's going to sound almost like problem number 7. It says at $15 per hour, how much will it cost for 20 minutes? You see, the trick now is the dollars are modifying hours, but the 20 is modifying minutes. You see, the problem that we have now is you're saying 20 minutes equals how many dollars? So you say something like, gee, I want to get rid of the minutes and bring in the dollars. But I'm not given the relationship between minutes and dollars. I'm given the relationship between hours and dollars. How do I get hours in this? Am I supposed to know the constant rate of minutes per hour? Yes. I'm supposed to know that there are 60 minutes in each hour. See, now what that does is the minutes now cancel out, and the label is what? Hours. I want the label to be dollars, so I know I'm not done yet. Here again, we come to a neat trick. Very often, the way we solve problems in life is we do the same thing several times. In other words, it's one step at a time. See, I've converted minutes to hours. What do I want to do next? Now I want to get rid of the hours and bring in the dollars. And what's the relationship? It's $15 per 1 hour. And you're going to get plenty of practice on this in the module. But do you see how this thing works? The minutes canceled, the hours canceled, I'm left with dollars. In calculus, we call this the chain rule. You see, we figured out how to convert from minutes to hours and from hours to dollars. Hours were the link, or the chain, that linked minutes to dollars. Now we multiply all the numerators, so we still get the same thing that we would have done wrong before. We still multiply the 15 by the 20 to get 300. But what happens now? There's a 60 in the denominator. 300 divided by 60 is 5, so the answer to this problem is $5. And does that make sense? Isn't 20 minutes 1/3 of an hour, 20/60ths? And if you're using 1/3 of an hour at $15 for a whole hour, it should be what? Unless there's a minimum rate that they charge you, for 20 minutes you should only be paying what? 1/3 of an hour, that's 1/3 of $15. That should come out to be $5. And again, if you want to do this in terms of dimensions, suppose the person is, should we call it dimension blind? All the person sees is the 15 and the 20. And says, I'm just going to multiply them. Great, multiply them. But read the label and see what you got. The 15 modifies dollars per hour. The 20 modifies minutes. The label would be, and get this one, dollar minutes per hour. You see, nothing canceled here. You can multiply the 15 times the 20, but you don't get a simple unit here. See, what you could have said was what? Another name for an hour is 60 minutes. I now replace 1 hour by 60 minutes. Now will the labels cancel here? Sure. And 15 times 20 is 300, divided by 60 is 5. That will give me the right answer. Another guy said, well, I don't understand why you did it that way. Why couldn't we have changed the minutes to hours instead? You could have. Isn't 20 minutes the same as 1/3 of an hour? Sure. Replace 20 minutes by 1/3 of an hour. Now the hours cancel. What's the answer? $15 times 1/3. 1/3 of 15 is 5. Again, I don't care which way you do it. I want you to have a comprehension of the problem and an understanding of what's going on. That's all we're going to be doing in all these problems. The worst that's going to happen is two things. One is the numbers will become messier, and they better become messier because I'm asking you to use a calculator. And if I don't give you nasty numbers, why should I ask you to use a calculator? Okay? And secondly, some of the applications are going to seem a little bit strange to you, but just like with physical exercise, if it doesn't hurt after you exercise, you either were in better shape than you thought you were in, or you didn't exercise hard enough. If I don't give you problems that somehow make you a little bit anxious, the chances are you're not extending the frontiers of your knowledge. So let's just go on here and see what happens. Here's a problem. It says at a rate of 45 miles per hour, how long will it take you to travel 81 miles? Have you ever had that kind of a problem? You know you can go 45 miles an hour. You look at the atlas, they tell you it's going to be 81 miles. Has it ever occurred to you to say, gee, I wonder how long it's going to take? Well, that's not such a bad problem. Oh, in fact, before you even start this problem, if you go 45 miles in 1 hour, how far will you go in 2 hours? At a rate of 45 miles per hour, in 2 hours, you're going to go 45 miles twice. That's 90 miles. That's more than 81 miles. So it tells you what? Even without knowing fractions or ratios or dimensional analysis, if you just don't panic and you're willing to think, you say, hey, I don't know what the exact time is, but it's going to be less than 2 hours. You see, because in 2 hours, I'm going to go 90 miles. I only have to go 81 miles. But why settle for an approximation when you can get the exact answer? Especially on shuttle flights and stuff like this. I mean, to round off to the nearest light year doesn't really help people that much. What we say is what? We want to travel 81 miles, that's the given, but we don't know how long it's going to take. So we say what? 81 miles equals blank hours. Then what do? we want to get rid of miles, and since it's in the numerator, we put it into the denominator. We want to introduce hours. See, now the labels will be right. What's the connection between miles and hours in this problem? In this problem, it says you go what? 45 miles in each hour. So what's the answer to this problem? It's 81 times 1 over 1 times 45. That's 81 over 45 hours. And by the way, on a calculator, how would you do this? You would take 81, press the division sign, enter 45, press the equal sign, and the answer would be what? 1.8 on the calculator. But what would the label be? 1.8 hours. And I'm going to come back to that in a minute. Let me just show you the long way of doing this without a calculator. 81 is 9 times 9. 45 is 5 times 9. Canceling the 9s, see? This is 9/5 of an hour. Now let's use all that stuff, good stuff that we learned in Module 6. Write this as a mixed number. 5 goes into 9. See, 1 4/5 time. So the answer to the problem is what? 1 4/5 hours. Isn't 4/5 the same as 8/10? See, 1.8. And here's where people make mistakes, and one of the reasons why the metric system is so nice. You know how a lot of people read this? They say it's 1 hour and 8 minutes. 1 hour and 8 minutes. Under what conditions would it be right to say that this was 1 hour and 8 minutes? See, what's the name of this column? It's tenths. See, if there were 10 minutes to an hour, 1.8 hours would be 1 hour and 8 minutes. The trick is, see, 1.8 means 1 plus 0.8. And an hour, see, what's the answer here? It's 1 hour plus 8/10 of another hour. If you want to convert to minutes, see, the 0.8 is modifying hours. What's another name for an hour? 60 minutes. So you're taking 8/10 of 60 minutes, 4/5 of 60 minutes. See, and 4/5 of 60 minutes is 48 minutes. In other words, the answer to this problem would be 1 hour and 48 minutes, which checks with the idea that the answer should be somewhat under 2 hours. And to check this thing the long way, see, in 1 hour you went 45 miles. How far would you go in 4/5 of an hour? See, every hour you're going 45 miles, so in 4/5 of an hour, you're going to go 4/5 of 45. 45 divided by 5 is 9. 9 times 4 is 36. So you go 36 miles in 4/5 of an hour. Then you went 45 miles in a whole hour. So in the hour and 4/5, there's your 81 miles. Do you see how, I'm not saying it's easy, but do you see how it's the same pattern over and over again? Remember in our introductory lecture, we talked about how language was difficult because the rules kept changing? You know, at least in math, you don't say that 3 plus 4 is 7 except after 9. I mean, the rules stay the same. And if you bear with me and learn to understand these things, the worst that people can do is mess up the problem for you by giving you nastier numbers, which the calculator takes care of for you, or nastier labels, which dimensional analysis takes care of for you. Either way, you can't lose. Here, let's do another problem. At $47 per coat, how many coats can a merchant buy for $1,000? See, I've used slightly nastier numbers here. And how are we going to do this problem by dimensional analysis? We say $1,000 equals how many coats? We want to get rid of the dollars and bring in the coats. And since it's $47 per one coat, you see what I'm doing over here? The dollars are going to cancel. And what does this problem say? It's 1,000 times 1, which is 1,000, over 1 times 47, which is 47. So it's 1,000 over 47. And now, even without the calculator, by longhand, I can find out what? That I can buy 21 coats, and I have a remainder of what? $13 towards the next coat. And you can check this out here. 47 times 21 is $987, plus the $13 change is $1,000. By the way, suppose you did this problem on the calculator, and every calculator is a little bit different. On my calculator, I took 1,000, I divided by 47, see, dollars per coat, etc. And I found out that I could buy 21 point, get this, 276,59574 coats. Well, this is a fraction, so I could buy what? 21 coats. The question is, what is this number? That's not the change. That's the fractional part of a coat you could buy. In other words, if you want to be technical here, you can buy 21 whole coats and this fractional part of another coat. How do you buy a fractional part of a coat? Well, the coat costs $47, so you're buying that fractional part of $47. If you were to take your calculator and multiply this messy decimal by $47, you get the same $13 that we got the other way. See, even the calculator requires interpretation. Here's a real mess. You can buy 2 3/4 pounds of meat for $4.95. At this rate, how much would 90 pounds cost? Well, that's a unit pricing thing again. Why not find out how much 1 pound would cost, see, dollars per pound, and multiply that by 90? See, dollars per pound. Haven't we done this problem before in our other modules, only with simpler numbers? See, we're going to take what? Dollars per pound and multiply that by 90. Well, what are the dollars per pound here? The dollars is 4.95. The number of pounds you can get for $4.95 is 2 3/4. So the dollars per pound, see what we're doing here? We're going to take the dollars per pound and multiply that by the number of pounds. That will give us the number of dollars. Well, again, there's lots of ways you can do this. In fact, you can even make estimates here. You can say this is around $5, this is around 3 pounds. $5 divided by £3 is around $1.60, $1.70, something in there. So you can round off. But if you want to do this from a completely mechanical point of view, all you say is what? 4.95, without the decimal point, that's 495 over 100. 2 3/4 is 11/4. How do you divide? You invert and multiply. So the problem becomes 495 over 100 times 4 over 11. 4 goes into 125 times. 11 goes into 4. Let's see how many times 11 go in here. 11 goes in here, whatever. It goes in here 4 with a 45. Then 5 goes into numerator and denominator. The answer is 9/5. 9/5 what? 9/5 dollars per pound. Oh, it's hard being a superstar. Anyway, bear with me. Again, this is what? $1.80 a pound. You're buying 90 pounds. That's going to be $162. All right? And again, if you wanted to do this in terms of fill in the blank, you're saying 90 pounds equals blank dollars. So you want to get rid of pounds and bring in dollars. And the only thing that makes this problem harder than the previous problems was that we have funny numbers here. They're not simple whole numbers. 2 3/4, 4.95. But again, if you have a calculator, see, 2 3/4 pounds is 2.75 pounds. On the calculator, you enter 4.95, press the division symbol, enter 2.75, hit the equal sign, and what lights up is 1.8, and then you have to interpret that that was $1.80 per pound. And if you don't understand this part, what good is the calculator? Because you'll just get the wrong answer, as we'll see in other examples coming up. Another problem. A radio is marked $87 plus tax. If the tax is 5%, what is the total cost? And here, I want to get away from the dimensional analysis and show you how, if you're frightened by words like tax and tax included, don't be afraid to go back to Module 1 and count like a baby. Look, to say that the tax is 5%, 5% means what? 5 cents on the dollar. So if the marked price is $1, the total price is going to be $1.05, right? So if the marked price is $2, you're going to pay $1.05 twice, which is $2.10. If the marked price is $3, you're going to be paying $1.05. See, for every dollar, you're paying $1.05. So for $3, you're paying $1.05 3 times. This is not my day, okay, which is $3.15. Do you see the relationship between the marked price and the total price? This is how mathematical formulas are born. You observe things and write your own shortcut. You notice that this column is the multiples of 1. And you notice that this column is the multiples of $1.05. And basically what this problem says is, when the marked price is $87, what's the total price? What this problem says is, when you're in the 87th row over here, the 87th multiple of 1, what's the 87th entry in this column? See, you want what? You want the 87th multiple of $1.05. That's $1.05 times 87. And the way you get it is you say, look, whatever the marked price is, I times that by 1.05 to get the total price. And in this problem, they tell me that the marked price is $87. See, that's reading comprehension. I have to see where the 87 goes. It's $87 times 1.05. I multiply this thing out, and I get $91.35. And in fact, Some people say, couldn't you have taken the 5% tax first and then added it on to the $87? And the answer is, I did. Only I did it so smartly, you never even noticed it. I used the distributive property, and I forgot to tell you. Because you see, $1.05, isn't that $1 plus 5 cents? So what I really did over here was the 87 multiplied the dollar, and the 87 also multiplied the 5 cents. The 87 times 1, that's my $87. That's the regular price. The 87 times 5 cents, that was $4.35. Now I can take the $87 and the $4.35, add them up, and that's the same $91.35. But look how I can do this. If worse came to worse, how they say it, if push came to shove, couldn't I have just listed all 87 multiples here and all 87 multiples here? That's what a computer sometimes does. It just lists things very, very rapidly and stops when it gets to the right answer. Now, let me show you how important reading comprehension is. The next problem is the same kind of a radio, only this time the price is marked $91.35, tax included. That means the 5% tax is already thrown in here. Okay? Now they're saying, what's the price of the radio without the tax? You see, it's the same thing we said before. Here's what I want you to see. It's still what? If the marked price is $1, you're paying $1.05. If the marked price is $2, you're paying $1.05 twice, which is $2.10. $3 would be $1.05 3 times, which is $3.15. Here's the difference. Here's where the reading comprehension comes in. This says that the $91.35 already includes the tax. Therefore, what column does that go into? Not this one. This is the one that doesn't have the tax on it. See, the 91.35 isn't here. See, what you're saying is, if you count by $5s in this column, and you're counting by ones in this column, when you come to $91.35 in this column, what number is in this column? And can you see where that will drive anybody but a math-oriented person a little bit crazy? So to say, to be a good mathematician, you don't have to be crazy, but it helps a lot. In any event, this is exactly the same formula as before. It's still the marked price times 1.05, $1.05, gives you the total price. The only difference is, and see, the calculator won't help me here. I've got to put the $91.35 in the right place. And the right place happens to be in the total price column, because it's the 91.35 is the total price in this case. Now when I fill in the blank, you see it's the marked price that's missing. This looks like a multiplication problem, but because one of the factors is the blank, that tells me that I've got to divide, not multiply. And by the way, there's a good way of figuring this out in your head. Not the right answer, but the right concept. When you add the tax on, shouldn't the item cost more, not less? See, in other words, if the price is tax included, whatever answer you get, it should be less than the price with the tax included. Don't ever be afraid, even when you can't analyze the whole problem, to be able to figure out what's plausible. In an era where many, many answers can be wrong and no answers are right, some wrong answers are less plausible than others. In other words, you do not have to know the right answer to be able to recognize when something isn't the right answer. That's a very, very important concept that many people don't understand. Sometimes you solve problems by eliminating all the impossible situations. For example, one way of finding out what you should be doing with your life is to find out what you shouldn't be doing with your life. That's why I love this course. If this course helps you, you're going to become so good at math that there are going to be all kinds of new horizons for you. If the course doesn't help you, you're going to know a new area in which not to pursue any longevity plans. You'll say, thank God for Gross. He taught me to keep away from mathematics. Now I'm going to be happy with my $3.75 an hour. Okay? So either way, you can't lose. Stick with me. You'll be wearing rocks the size of diamonds. Let's go ahead and take a look now what's happening over here. You see, this looks like a multiplication problem. It's a division problem. And the answer when you divide 91.35 by 1.05 is $87. And you can do that part on the calculator, but the calculator doesn't tell you you're supposed to divide. The calculator is a non-communicative device. It does not talk to you. It is antisocial. The calculator won't do a darn thing unless you tell it specifically what to do. And if you punch in the wrong numbers, it doesn't say, hey, dummy, you want to check this? It just does it. It's obedient. Okay? It's not interactive, let's put it that way. Let's just check the answer here. See, if the regular price was $87 and I'm paying $1.05 for each dollar, that certainly does come out to be $91.35. And again, let me show you why you mustn't use the calculator without reasoning. A lot of people on the calculator take 5% of the $91.35 and they say that's the tax. Then they add that on. No, they subtract that from the $91.35. Do that. I'm not going to take the time now because my time is almost up. Not my time, the period. Hopefully. I heard a man being interviewed on the radio and they said to him, have you lived your whole life in New York? And he said, not yet. I hope my time is not up, but the period is coming to a close, so let me just have you do this on your own. Actually take 5% of $91.35. And whatever that is, subtract that from $91.35. You won't get the right answer to this problem. And how do I know that? Because we already know that 87 is the right answer. Any answer you get this way won't work. And the reason for that is you don't pay tax on the tax. Let me give you an example. You go into a restaurant and you buy a meal for $10. You're going to pay 5% for a sales tax, say, and 15% for a tip. That's 20% altogether. 20% of $10 is $2. So the whole bill is $12. When you want to find out what the meal costs, you don't take the 20% off the $12. See, that gives you $2.40, not $2. See, you only paid this tax on the $10. See, what you're supposed to say is, look, for every dollar I paid for the meal, it cost me 20 cents more. So I'm paying $1.2 per dollar. So 1.2 times blank equals 12. Blank equals 12 divided by 1.2, which is 10. You see, I'm not asking you to agree with me that I'm doing the problem right. I want you to see that if you actually did the problem this way, the calculator wouldn't say don't do this. It would simply give you the wrong answer. You didn't pay $2.40 for tax and tip. You paid $2. I think we have time for one more problem. Better have, okay? At 40% off the regular price, a radio costs $84. What is the regular price of the radio? Well, you see, we got numbers all over the place. 40%, $84. What are these things modifying? The 40% is off. Off what? Off the regular price. Off the wall, the way I'm going right now. And what's the $84? Is that the regular price? No. Read the problem. It says at 40% off the regular price, a radio costs $84. So the $84 is what? The sale price. I says, wow, I didn't want to take a reading comprehension course. I just want to do math. Well, this is the whole point. You can't do math unless you can read the problem enough to analyze what's asked for. Because if you're not careful, you'll wind up with what? The wrong answer because you may have done the wrong problem. Let me just go on with this. See, the regular price is $1. What does it mean to say it's 40% off? That means for every $1, they're taking 40 cents off the price. If they're taking 40 cents off the price, 60 cents is still on the price. So if it was $2, they're taking 40 cents off twice, and you're paying 60 cents twice. If it was $3, they're taking 40 cents off 3 times, which is $1.20, and you're paying 60 cents 3 times, which is $1.80. Do you see how easy this is? I can make up a table like this for my salespeople, so they won't even have to do any arithmetic when the customer comes in. But now, let's see how the on price, by the way, that's what you're still paying. See, that's the sale price. Now, the thing is, we want to relate the regular price to the sale price. I don't have to give you the formula. If you understand what you're doing, you will invent the formula yourself. Look at, this is the multiples of 1. This is the multiples of 40 cents. This is the multiples of 60 cents. In other words, how do you get from the regular price to the sale price? Whatever the regular price is, you only multiply that by what? 0.60. Do you see that? This is 0.60 once, 0.60 twice, 0.60 3 times. See, 0.60 4 times. That's why we made all this fuss over multiples. These are the multiples of 60 cents. When I'm on the 8th row over here, I'm going to be on the 8th multiple of 60 cents. That's $4.80. I don't need any tables. I don't need a calculator for that. I don't need a formula for that. I will make up my own formula. And it tells me that what? The regular price times 60 cents. I just abbreviated that to 0.6. Do you understand it's the same thing? See, the regular price times 0.60, don't even need that in there, is the sale price. And where does the reading comprehension come in? What do I replace by 84? The regular price or the sale price? The sale price. Because it says, at 40% off, it costs $84. So now I go over here, and I replace the sale price by $84, that leaves me with blank times 0.6 is 84. That means blank is 84 times 0.6. That's 84 divided by 0.6. I can do that several ways. I can move the decimal point one place in the numerator and denominator. I don't need my calculator for this. But if I had the calculator, all I have to do is what? Enter 84, hit the division sign, enter 0.6, hit the equal sign, there's the answer. And how can I check that this answer is right? At 40% off, that's 0.4. That's $56 off, isn't it? And if I subtract $56 from 140, I get $84. That's the most important thing I can teach you right now. Well, there's lots of most important things I can teach you, but right now, this is the one that's most important. Tomorrow, it'll be something else. Whenever you get an answer, don't look for the back of the book. You can if you want to. How should you know whether an answer is right? If you stick it back into the problem, it should work. Now, let me show you the danger with a calculator, and we'll conclude on this note. Many people take the 0.6 and multiply that by the 84, and they get $50.40 for the answer. That's ridiculous. If the sale price is $84, what kind of a sale is it if it costs more than the regular price? See, again, you have to understand that what? You're not going to buy at the sale if it costs more at the sale than the regular price. So somehow this should warn you. See, what you did over here is you put the 84 in the marked price column. What you said was, if the regular price is $84, then on sale, it's going to cost me $50.40. That's great, except that the problem said the sale price is $84. What you have done here is you have found the right answer, but to the wrong question. And boy, let me tell you, in my opinion, that one of the biggest problems that we have in the world today is people finding the right answer, but to the wrong problem. Make sure when you're solving a problem that the answer that you get solves the problem you were trying to solve. And by the way, I don't just mean that in mathematics. I mean if it's a social problem, an economics problem, a community problem, first make sure you recognize the problem so that you know what it is that you're solving. Don't go and solve something that's totally unrelated to what you're trying to do. It looks good, but it doesn't get anything done. And that just about plumb tuckers me out for this particular time. So as usual, I give you the same admonishment. The best I can do is help talk you through the module. Now read the module, do the check the main ideas, do the mastery review, work on the self-tests, and I'll see you again when we do self-test 9, Form B. Until that time, have fun, study hard, and stay young.